I bet.
Okay. Let me talk about the homework for a second. There's quite a few problems that you may have struggled with. And I am going to address some of those types of questions, and also limit problems with from one-sided limit algebraically. We haven't quite gone over that, so hopefully after today's lesson, you'll be able to, hopefully I'll answer some of the questions that you guys may have about the homework. Good. So in your packet, let's go to we're going to be on page 14. But you can just kind of stay on that page. I want to just kind of recap some of the things that we did yesterday. Okay, so one thing that we did yesterday was, well, we focused on the concept of continuity, and we addressed how to deal with continuity conditions when working with piecewise functions. And with piecewise functions, we stepped through the conditions, but we knew that if there's a piecewise function, if there were connected graphs on either side of our target, we have to spend that extra effort to find the one-sided limit coming from both sides of the target. And then if they are in agreement, we know that the second condition will pass. If the one-sided limits are not in agreement, we stop the problem, we say the limit doesn't exist, and we know it's going to be a non-removable discontinuity. We also saw problems that look like this. So on page 13, we saw a problem where the piecewise function looked a little different. And the reason that it's different is because our restrictions are different. We have to understand that the x plus 5 is just a point, and we never take a limit of a point, right? There's nothing for us to move for. So we never want to do a limit of a point. We only want a limit. We want to apply a limit for a connected part of graph, and that is only going to be with this first function. So this is basically saying that this is the entire graph. The only place that it doesn't exist is at 2, and that 2 is being defined potentially elsewhere by a point. So this is the notation that you're going to see if it's this type of problem, but you can always rewrite it in a way that can feel more just more familiar, right? So what you could do is you can write that x squared minus 4 over x minus 2 as the same function, but on either side of 2, right? Because this doesn't equal to 2 means that it exists to the left of 2 and to the right of 2. It's just that at 2, it's something else. And then once you have it in this form, then it feels just more familiar because you know that the point is the one in the middle, and then the limit is the same function. So you just rely on one limit statement and you just continue going down your conditions. Okay. And then we also talked about intermediate value theorem. And the whole purpose of intermediate value theorem is what is needed if we didn't have the graph in front of us, what is needed for us to guarantee that a function hits a particular y value? And if we want to just narrow it down to the most minimal information that I need to guarantee that y value, then I need 3 things. I need to know that the function is connected all the way through in that interval. And then whatever my target y value is, I need to confirm that one of the endpoints produces a value below our target, and then the other endpoint produces a value above my target. And if I have these 3 pieces of information, I can guarantee that whatever target that we're looking for is going to be reached. Okay. And that's really all IVT is, right? We want to guarantee a y value, confirm that it's continuous, confirm the endpoint it has a y value either above or below, confirm that the other endpoint has a y value that's on the other side of the first endpoint. Okay. Good. So on page 14, we're going to do two more piecewise functions involving continuity, but these feel a little bit more strange because we're trying to solve a variable that will allow for continuity to occur. So let me read the directions first, and then we'll step through it. Okay, so directions say, make a function continuous. In these exercises, find the constant a or the constants a and b such that the function is continuous on the entire number line. Okay, so the way that you approach these problems, anything dealing with continuity, you just go through continuity condition. Okay, if you follow through continuity condition as it's spelled out, you're just going to be able to come across whatever you're solving for before you even realize it. Okay, so if you just step through continuity condition, whatever you're looking for is you're going to be able to find it as long as you step through what the conditions ask you to do. Okay, so we're just going to follow the continuity conditions for our problem, and we're going to kind of just go through one by one. Okay, so the first thing we need to determine is what is our C value? What is our C value? So what do you guys think that is? 1, right? So you always look at the right side, look at where that restriction is. Where does the graph begin? Where does the other one pick off? That is where a potential break could be. That's our C value. So our C value is 1. Okay. Okay, good. So now we're going to step through the rest of our steps here. So condition 1, we want to find f of 1. Okay, which one do we choose? First or second piecewise? First one, right? We see the equal sign is with the first piecewise. So we're going to insert 1 in for x. What do we get? 3. Okay. And we also learned from before that whatever we get, we're going to keep going with the for first one. Okay. Okay, I do want to point out that we're trying to force continuity out of this. So basically what we want to do going into this is we're trying to make every condition pass. Okay. And we're trying to figure out what do I need to get the condition to pass. So I'm going to go through each of the conditions and assume that I'm trying to get them to pass. Okay. Second condition, does the limit exist? Do we rely on one limit statement or do we need 2?
2.
We need 2, right? We have 2 different functions on either side of 1. We need 2. So just going to follow what this says. Limit as x approaches 1 from the left side of 1. Okay, so from the left side of 1, which is appropriate for that? First or second? Second, because less than 1, right? So think of values less than 1. That's what we need. So ax minus 4, we can worry about that later. Let's step off to the side and do the other limit from the other side. 1 for the right side of 1, that's going to be the first piecewise because of the restriction here. Okay. Let's evaluate the limit. Replace 1 in for x, and what do we get with the first one? A minus 4. Okay, so have that there. Come back to it when we need it. Okay. How about from the other side?
3.
Plug 1 in for x, we get 3. Okay, now we want each condition to pass. So what do we need for this to have? What do we need for between these two one-side limits? We have to get them to equal to each other, right? If we want the function to be continuous, we have to get them to equal to each other. So we'll set them equal to each other. Okay, so now we have an equation in front of us. Can we solve for A? A equals, that's all we need. All right, so we didn't have to do too much, right? If we just follow the directions, we're going to eventually solve for whatever variable that the problem is asking for. Okay. Any questions? Okay, 66. Okay, what's different about this setup?
You have an x equals a.
You got x equals a, you got x doesn't equal to a, and also, yeah, so yeah, two things, right? One is this feels strange, right? Having that value not being a known constant, but it's kind of like that unknown constant. And second, the inequality feels different, right? The restriction feels different. It's not less than greater than, it doesn't equal to and equal. So if we want, we can rewrite this in a form that feels more familiar. We know that the x squared minus a squared over x minus a, that's where the function is, that's where the graph is. So we can say that doesn't equal to a means the graph exists to the left of a and it exists to the right of a. Again, you don't have to do this, but I think for some of us, it just feels like it just makes more sense to see. It feels more straightforward rather than seeing that doesn't equal to a. Okay, so doesn't equal to a means the same thing as the function exists to the left of a, and the same function exists to the right of a. Okay, so first things first, what is our c value? A. Okay, so it's an unknown value, but we're just going to go through the process. All right, let's follow the conditions here. F of c, our c is a, so f of a, what's f of a equal to? 8, right? If I insert a into the expression, there's no variables for me to plug in. It'll stay 8 no matter what I do. So I don't know what my a value is yet, but I'm just gathering information. Second condition, does the limit exist? Okay. Can I rely on one limit statement or do I need two? One is enough, right? And we do not touch the 8. We don't touch the point. We only work with the graphs. And we could do one-sided limits, but these are the same functions. We would just be duplicating our efforts, so we don't have to. We can just rely on one limit statement. Okay. Limit as x approaches a. My expression. Okay. Feels a little strange that x is approaching a value that we don't know, but sorry, it's an arrow. But we're going to treat it like we normally would, and what would you do with an algebraic limit problem? Before factoring. Plug in a. Plug in, right? Let's plug in a for x, and let's see what happens. Okay, so a goes in for x squared. What does that get us? A squared minus a squared is 0. Denominator 0. So we know there's a hole. We know there's more work to be done. We know we can remove factors, and we know that we should be able to get down to something that's other than 0 over 0. Okay, so factor. What can we do with x squared minus a squared? What does that factor be?
X plus a, x minus a.
Good, difference of squares, right? So x minus a, x plus a, all over x minus a. Right, do we see the cause of that 0 over 0? We do. We can remove it. But we still have to reevaluate. So what do we get?
X plus a.
We got to insert a in for
Oh, 8.
x.
or X, yes.
Yeah, A in for X, so what do we get?
2A.
Get A plus A, which is equal to 2A. Now, we still haven't solved for A yet, but we do have a limit. The limit is 2A. Do we keep going?
Yes.
Yes, okay, so we didn't get it does not exist, so we're gonna keep going if we don't get it does not exist. So third condition, what's required from the third condition? Good, so we look at the first two conditions and we see what information did we gather. So the result of the first condition is 8. The result of the second condition is 2A. I'm trying to force continuity, so if I want to force continuity, what must happen? It has to be equal, right? 2A must be equal to 8 if I want all three conditions to pass. And we have an equation that we can solve simply by following our conditions. A equals what?
4.
4. There we go. That's our A value. So something that feels complicated, if you just step through continuity conditions and just follow what it says, you're going to arrive at your whatever you're looking for simply by following your conditions.
And do we need to prove that in any way or step through the proof?
On the AP exam, if they ask you to justify your answer, if you step through your conditions, that's justification.
Okay.
That's justification. Okay, any questions? Okay, so some of this appeared in your homework and you may have been confused, but hopefully seeing us go through it, answers some of your questions. Okay, so today we're going to be talking more about limits, vertical asymptotes, and limits that doesn't exist. Okay, because there's more details that we can gather besides just the limit doesn't exist. Okay, let's go to page 15. Okay, so let's think about algebraic limits that we practiced in the past. So let's say limit as x approaches c of f of x, and we knew the first thing that we did was to plug in, and let's say we plugged everything in, and then we realized that it was 10 over 0. Okay, just a random example. Okay, so if you get 10 over 0 or 8 over 0 or 5 over 0, what conclusion did we make? Vertical asymptote. And because there's a vertical asymptote, what do we say about the limit? Okay, good. Undefined or limit doesn't exist. But we stopped there, right? We didn't go any further because we had our answer and we moved on. But there's more to explore. And the reason I say that is because we know the limit exists. We know the limit doesn't exist, and we kind of have an idea how the graph may look. That there may be an asymptote, but we don't know exactly how the graph is moving, right? Maybe one's going down, maybe one's going up, maybe they're both going up, maybe they're both going down. Right? We don't know exactly how the behavior of the graph around that asymptote. And before, we didn't really care. We're just like, okay, we got limit doesn't exist, and we move on. But today, we're going to do one-sided limits of an asymptote without the use of a graph, and we're going to try to determine how the graph looks on either side of that asymptote without the use of a graph and relying on algebraic steps. Okay, so that's what we're working towards. We already know that limit doesn't exist, but then we're going to try to find out more information about how the graph looks around that asymptote. Okay. So let me go through some notes here. Infinite limits. This is a limit where the function increases or decreases without bounds. The arrows are either going up to positive or negative infinity. If the limit approaches from either the right or the left and it approaches positive or negative infinity, then we know that there must be a vertical asymptote, because anytime that it hits a wall, we know what's happening, that there must be an asymptote. Okay, so how do we spot a vertical asymptote if we're looking at an expression? Well, first, confirm that it's a rational function. So basically, we're focusing our attention in the denominator. If the denominator has no factors that cancel, then there's a vertical asymptote. So if we want to find out any vertical asymptotes, we always look in the denominator to see if there's any variables in the denominator that does not have a matching pair in the numerator for us to cancel out. Okay, vertical asymptotes always comes from the denominator. So let's look at example 1 here. It says find all the vertical asymptotes of f of x. And I also want to bring in some related information about this function. So if I want to find vertical asymptotes, it's a lot easier if I can get everything in factored form. So I can match the components a little bit easier. So let's factor the numerator and denominator separately. Okay, x squared minus 3x plus 2. Multiply to be 2, adds up to be negative 3. What are our factors? Negative 2, negative 1. Okay, put that down. X squared minus 4, difference of squares. Okay. Now, do you see any factors that cancel out? Yes. And what does that tell us about what we can find here? That means there's a what?
There's an asymptote.
Not an asymptote, but a hole. Okay, so we know that any factors that cancels out is going to be where the hole exists. And the way you find the hole is you take that factor, set equal to 0, and you solve for x. So x minus 2 equal to 0, x equals 2. So we know that there must be a hole at x equals 2. Okay, a hole at x equals 2. Are we good with that? Okay. Now, do you see a factor in the denominator that does not cancel out? Yes, so this is where we look for the vertical asymptote. Okay, so if I set x plus 2 equal to 0, what do we get? X equals negative 2. Okay, so I can say vertical asymptote at x equals negative 2. So when everything is in factored form and there's a numerator and denominator and you got a rational function, we should be able to pick out these discontinuities, right? Holes, factors that cancel out in the denominator. Vertical asymptotes are factors that don't cancel out in the denominator. Okay. Now, this doesn't quite relate to what we're doing right now, but I want us to kind of have a big picture idea. Anybody know what this x minus 1 tells us? Not a hole, it's not an asymptote, but it's a feature of the graph.
The direction.
Huh?
Direction.
Not direction, something else.
Is it part of the function?
It is part of the function. It's a specific feature of the function. Yeah. Not y-intercept, but the x-intercept. It's the x-intercept. Okay. So it's not quite related to what we're talking about now, but I want to. It's good to know what every part of the function is giving information about. So if I set that numerator equal to 0, that's going to be where the graph exists on the x-axis. Sorry, on the x-axis. So if I set x minus 1 equal to 0, I get x equals 1. So that's a physical point on the graph, and that ordered pair is at 1, 0. So I just want to kind of spell out all the different parts of a rational function. Okay. But our focus today is on the vertical asymptote. Okay. So we have very specific steps as to how to talk about the one-sided limit on either side of the asymptote. I'm going to skip these steps for now. I'm just going to jump directly to the example, and then I'll step through the example, and if we need to, I'll spell out, I'll kind of point out some of the steps above. Okay, example 2, it says determine the limit as x approaches 2 for f of x. Okay, so we're just going to approach this problem with the methods that we have been using and see what happens. Okay, first things first. What do we always do? Plug in, right? We don't try to do anything else. And the reason why it's so important for us to plug in is because there's going to be different paths that we could take. And we don't want to go down the wrong path until we get confirmation that that it is a specific category, right? We got to categorize it before we make assumptions. So I'm going to insert 2 in. What do we get? 3 over 0. Okay. 3 over 0. Now this tells us something very, very specific about what's going on. So what can we conclude?
It's just vertical asymptote.
Vertical asymptote. And therefore the limit does not exist. Okay. So in the past, we would go ahead and stop because we already found the limit. Well, the limit doesn't exist. But we're going to go a little further. And like I said before, we're going to dig a little deeper about what's happening around this graph. Okay. So we know there's a vertical asymptote at 2. So let me kind of give some possibilities of what the graph could look like. And I want to show you that there are 4 possibilities of what the graph could look like around an asymptote. So let me just list out all the variations to show that we have, that if we want to figure out what the graph looks like, we have a couple of variations to kind of sort through. Either the graph could both going towards infinity from both sides of 2. It's also possible that the graph could be both going down as we approach 2. It's possible as well that one could be going up and the other going down. And then vice versa, maybe from the left is going down and from the right is going up. So we're going to try to decipher between these 4 by looking at one side of the limit. Okay, so right now we know limit doesn't exist, which is fine, but I'm going to extend this problem and have us look at the limit as we approach 2 from the left side of 2. Okay. And I want us to approach this problem from the very beginning. Like I said, we haven't seen anything before, so we're going to start at the beginning, and I want to kind of talk through the entire process. Okay. First thing, plug in 2. Okay, so we're plugging in 2, and again, we get 3 over 0. Okay, we know there's a vertical asymptote. We know the limit doesn't exist. But now what's different about part 2 is that, oh, this is not asking for the full limit anymore. This is only asking about the one-sided limit from the left side of 2. So what are our options? Either the graph is going to head towards what? Or
Negative infinity.
so we know, okay, so we don't want to say the limit doesn't exist because it's not asking for the full limit. It's only asking for the behavior from the left side. And we know we're down to 2 options, right? Our answer will either be positive infinity or negative infinity. Now, if we had the graph in front of us, we could just easily tell, but we're trying to do this numerically, algebraically, without the use of a graph. And if we're choosing between our 2 options here, this is the method that we're going to practice using. Okay, so this goes up to the step we have here. To further evaluate one-sided limit, especially if we know that we're choosing between positive and negative infinity because there's a vertical asymptote, we're going to test a decimal 0.1 to the left of the argument x value. We want to choose a value from the correct side, but then also value close enough so that we can get a good reading on how the graph is behaving. Okay. So what's a decimal value that is 0.1 to the left of 2? Because I got to approach 2 from the left side of 2.
1.9.
Okay, so we'll test x equals 1.9. Now, I want to prove to you and show you that we can do this without a calculator, okay? Because we're not going to ask for the, we don't really care what the decimal value is. We just want enough information to narrow down between these 2 options. Okay, so we're going to test 1.9 because our whole purpose is to figure out which one of these options to choose. Okay, so insert 1.9 in for x. Now, all I care about is whether each of the numerator and denominator is giving me a positive or negative value. Okay, so we don't care what the decimal value is. What's 1.9 plus 1? Positive or negative? Positive. Okay, so again, I don't really care about what the decimal value is. I just want to know whether that value is positive or negative. Okay, how about 1.9 minus 2? Negative. So doesn't matter what the value is, but if I have a positive divided by a negative, I'm always going to get what?
A negative.
Negative. So if I know it's negative, that's going to help me narrow down my option. I know I'm choosing negative infinity. So I know that my graph is going to be one of these two options, right? It's either, I don't know what's happening on the right side, but I know the left side is this, it's going to look like this. One of these two. Okay. Let me do a third variation. And now let's say the problem is saying limit as x approaches 2 from the right side of 2. Again, let's go through the steps like as if we haven't seen any of the previous problems. Okay, so just to kind of get into the habit, right? We're always going to insert the value first, gather information. Again, we get 3 over 0. We know that must mean there's a vertical asymptote. We know the limit does not exist, but that's not going to be our answer because we go back and we realize, oh, it's not asking for the full limit. It's only asking for the one side limit from the right side of 2. So again, there's only two options. It's either going to possibly be what?
Positive infinity or negative.
Yeah, because we know there's an asymptote. So if we're approaching an asymptote, it's going to be predictable in terms of how it's moving. It's either going to shoot up to positive or go down to negative infinity. So now that we're choosing between these two options, we have a specific test. So we want to choose now a decimal value 0.1 to the right of our target x value. So what is 0.1 to the right of 2?
2.1.
2.1. Okay. So let's go ahead and do that test. 2.1 plus 1 divided by 2.1 minus 2. Okay. Again, I don't care about the decimal value. I just want to know whether it's positive or negative. So numerator gives me positive. Denominator gives me
Positive.
positive. So positive over positive is
Positive.
positive. So we know that from the left it's going down to negative infinity. We know to the right it's going to positive infinity. We have an idea how the graph is going to look, right? It's going to look most like that. Okay. Any questions about this procedure? Okay. This tends to give students a lot of trouble. And let me talk about the reason why. The reason why is because now that we have in our heads that we're going to be using decimals, the tendency is now a lot of us want to just automatically use decimals as soon as we see one side limit. But sometimes the one side limit is there just to see if a student understands and is to potentially throw a student off. So what I want to stress to us is that we're only going to involve decimals if there's a vertical asymptote involved. Which means that if there's a hole, or if the limit does exist, it's like as if the one-side limit, it's like asking for the full limit. We don't even care about the fact that it's a one-side limit. We ignore the one-side limit. Because if there's a hole, or if the limit exists, then the one-side limit would be the same value as the regular limit. So we only do anything special with the one-side limit if there's a vertical asymptote. We have to kind of, and through next page when we do our practice, we need to keep track. We need to make sure that we understand our steps. Okay, we got to be disciplined and not get thrown off by those one-side limit. Okay? You're only going to do anything with decimals if there's a vertical asymptote, because the decimal is only there to help you decide between positive and infinity. It's not going to help you do anything else. Okay. All right. So the next page, That's why it's so important for us to go through the proper steps, because if we don't know which category that we're in, we could be potentially blindly going down the wrong path. All right, so next page, page 16. So number 3. First thing you do, if you see a one-sided limit, ignore that notation and just focus on the whole number. Okay. All right, what's the first thing that we can do? Plug in, right? Plug in -3. We have to know which category where we're in before we go too far. Okay, so -3 in for x. Okay, what do we get in the numerator? Numerator, 0, okay. Denominator, -7. How do we interpret 0 for -7? 0. And that's the answer. The one-sided limit doesn't play a role at all. It's only, we only go back and look at it if we realize there's a vertical asymptote and we have to make a decision. The reason why we ignore the one-sided limit is because the real limit is 0. So that means the one-sided limit is also going to be 0, right? So we don't have to do anything special. It's like as if we're asking for the full limit. So that makes sense. No decimals, right? No decimals with this problem. Okay, number 4. First things first. Plug in 0. And what do we get? 0 over 0. Okay. What does that? What does this tell us?
There's a hole in the graph.
There's a hole. There's a limit that's waiting for us at the end of the problem. We're going to be looking for common factors to remove. No decimals, right? Decimals is not part of our process here either. Okay, so factor. Okay, do you see common factors?
The x's.
X's. So we should be able to get to a real number without the 0 over 0 showing up again. And what do we get? -5. Again, I see enough students make this mistake, so I want to point this out. I think that, but I want to keep stressing that, this does, tend to allow students to do the wrong thing, right? Sometimes students get to this point, they say, oh, I see that one-sided limit, I gotta do a decimal, and they choose like -0.9, and they end up, or -0.1, they force it into a decimal, right? So again, we gotta stay disciplined and don't get thrown off by the one-sided limit until or unless a situation calls for it, right? So -5 is the limit. So -5 is also the same as the one-sided limit, right? So we don't do anything special with that one-sided limit. Okay, number 5. First things first. Plug in -2. Okay, what do we get? Okay. Now there's a what? Now there's a vertical asymptote. The full limit doesn't exist. And now we can go back and say, okay, now we know that it's not asking for a true limit. It's only asking for a one-sided limit. There's a vertical asymptote. And now I can choose between my two options. I don't know where it's headed, but I do know that I'm only down to two options. It's either approaching positive infinity or it's approaching negative infinity. Now we can do decimals, right? So the only time you do the decimals is if you get this far into the problem, you realize there's a vertical asymptote, and you're trying to decide between your positive or negative infinity. Now, we gotta be careful with the decimal here. let me draw a number line to kind of help us. So let's say this is 0, this is -1, this is -2. I need to choose a value that is slightly to the left of -2. So what's the decimal value to the left of -2? -2.1, right? Everything is opposite because we're on the negative side. So x, we're going to test. Okay. Again, we don't care about the decimal value. I just want to know whether it's positive or negative. Okay, numerator is positive. Denominator is negative. Therefore, we know the graph is going to look more like this. As it heads towards the asymptote, it's going to dip down and go down. Okay, try number 6. What do we get? Okay, 74 over 0. What does that tell us? Vertical asymptote, the full limit does not exist. Do we have to go any further?
Yes.
Well, we could, just so that we can figure out the behavior, but it's asking for the full limit, and we know the full limit doesn't exist, so we just stop there. Okay, it's not asking for how is the graph moving from the left or from the right. This is sufficient. Okay, does that make sense?
So if it were asking like specifics, then we'd go on, but if it doesn't ask for
That's
specifics,
right.
don't.
If there's no one-sided limits, we don't go any further than this,
Okay.
because we already know limit doesn't exist. Okay, good. So hopefully that clears up some of the questions that you guys may have when you're dealing with limits with one-sided limit. Tomorrow we'll practice through the rest of these problems so that we can kind of keep that process going. Okay, and then we have one more section to go over, 3.5, and we can start doing our test review. Okay, you guys have homework tonight as well. You guys can get your phones.